Alright, here's 6.1, discrete and continuous random variables. So we'll start with the warm-ups. What are discrete numbers? Well, they're integers. They're whole numbers that are negative, positive, and zero. What are continuous numbers? Real numbers. Decimals, fractions, repeating decimals, irrational numbers, everything except for complex numbers. How do we verify a probability model? The sum of the probabilities have to be equal to 1, and the probabilities all have to be between 0 and 1 inclusive. They could be 0, they could be 1. What is a random variable? This is very important. You need to know this. A random variable is a variable that takes a numerical value of a chance process. So it's a number, it's a variable that's a number of a chance process, a probability thing. What is a probability distribution of a random variable? Gives all possibilities and the probabilities of them. It's like a probability model. Same type of thing, but it's for random variables. Suppose you flip two fair coins, make a probability distribution for the number of tails flipped. Well, we can get tails, 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 heads, heads, tails, heads, heads. So, the possibilities are 0 tails, 1 tail, or 2 tail. 0 tails, well, it's this one right here, so 1 out of 4. 1 tail, here and here, so 2 out of 4, or 1/2. And we don't need to figure out this last one because 1 minus these two would give us this, but the probability of 2 tails is right here, 1 out of the 4. So that's our probability distribution. Make a histogram. So discrete data, we put the number right in the middle of the bar, and then we just make it up. It's pretty simple. Number 9, suppose we roll 2 fair die, record their sum, and make a probability. Remember our probabilities. They go from 2 to 12. They start at 1 over 36. They go up to 6 over 36, which is at 7, and then go back down. It's all symmetrical. And they, of course, reduce if we actually ask for a fraction. So that's our probability distribution. We'll look at that in a second. Next, we got a little bit too much going on here. Let me erase some of this. I think I was trying to prove a point there. Our mean is the same as the expected value, which is the probability, or a probability of a distribution, is on average what we expected each time we perform the probability model. So on average, that's why we get numbers that are not whole numbers, they're not integers, even though we're talking about discrete data. And the way we get our expected value is the x values times the probability, and then add them up. So we'll do some by hand, but we'll use some for the calculator. The variance, sigma squared, is used with this formula, but we're going to use a calculator, and I'll show you that. So let's play a game. If you roll a 3, 4, 5, 9, 10, 11, I will give you $1. So 3, 4, 5, 9, 10, 11, we give you $1. Here we are. That's our x value because it's a numerical quantity of a chance process. $2, $1, $1. If you roll a 6 or 8, no money's exchanged, so zeros. If you roll a 12 or a 2, I'll give you $2. But if you roll a 7, you owe me 3, so it's -3. So this is from your standpoint. So, is it worth for you to play this game? Well, we want the expected value, on average, what you are going to get. So we need the mean. So we're going to use a calculator. So we can put in our list of all the sums, but we're not using that as the x values because we don't care about that. We care about the money. The money is the x. And the probabilities are here. So L3 is our x values, L2 is our probability. So when we do our stats, we do stat, one variable stats. We don't just hit enter though, because that'll just do it for the first column. We want it for, actually I got to remember, L3, then L2, because L3 is our x, then L2 is our probability. We want it in that order. So L3, comma, L1. Oops, no, not L1. I don't think so. Let me double check. Always good to check. Our probabilities is L2. I don't know why I thought it was something else. So we'll go back to here, and we change L1 to L2. Then we hit enter. So our expected value is our X bar here, 0.111111 repeated. Our standard deviation is 1.4. It can't be this one because there's nothing there. And we can scroll back down and see all our mean. If we end up doing a calculation and then we can't scroll back up, remember we can hit second entry. That'll give us our last one. Second entry will give us the next one. And we can do it again without typing it all in again. So, and on the Inspire, same thing. I put in my X values and my probability, need to label them. And then statistics, stat calculations, one variable statistics, number list, 1, even though there's 2. And our X list is X, and our frequency list is our probability list, so P. The first result column just tells us where we're going to put them. Column C, it's empty, so that's fine. Hit enter. These are variable references. They're not the column, not column P or column X. It's all the way to the right. We're at A and B. So variable, and there we go. We get the mean. Obviously, this is undefined. It was nothing on the 84, and here's our standard deviation. So, on average, every time you play this game, you will get 11 cents. And this is from your standpoint. So I lose money, so this kind of sucks. So is it worth it for you to play the game? Yeah, because you earn 11 cents on average. Can you get 11 cents? Of course not. It's all done in $1, $2, whatever. But over time, you get 11 cents per game. So if you play this game 100 times, well, it's pretty simple. Figure out how much we owe or we make. It's 100 times 11 cents. So on average, we should expect to get 11, I guess, dollars and 11 cents because it was 0.11 repeated. So over 100 times, you should get about 11 bucks and 11 cents. Now, does that mean you're going to get that? No, not necessarily. It could be off. Now, what if I change that when you roll a 7, you owe me 4? Is it still worth playing? Well, we go back to our list. Edit our list. And then when it says -3, change it to -4 because I'm taking more money from you because I want to win. And then, really, we can do the same thing, same entry. And notice now our expected value, our mean, is negative. So from your standpoint, it means you're losing money. You're losing a nickel at 0.5 every time that you play. Now the Inspire, what's nice is as soon as you change it, it updates. So it's right there. So, is it still worth playing? No, because the mean or the expected value, we need to know those are the same. The mean is the expected value over time. That's what probability is. So you would lose 5 cents. If you play this game 100 times, how much money would you lose? $5. Actually, I guess you would be losing $5.55 since it's 5 repeated. So I get that extra 55 cents, and I want to make sure I get that. All right, so we're going to do the same thing here, but now we're going to do it with by hand instead of using the calculator. So we have an insurance company that sells a $250,000 one-year term life insurance policy to 17 and 18-year-old females and males. They charge $200 per year. Probability that a 17-year-old, so we'll just say teenage female survives the year is 0.9992721, which I looked up. Probability that a teenage male survives is 0.99329. Compute and interpret the expected value. Interpret. So tell me what it means after you find it. So from the insurance standpoint, from the insurance company, so there's two options. You can live or you can die. So if we look at the females first, if you live, the insurance company gets $200 because you pay the $200 and nothing else happened. And the probability of that happening is 0.999721 because that's what it said. So we multiply straight across. Now, if you die, unfortunately, you've already paid the $200, but the company has to pay out $250,000 on top of that. So negative $250,000 plus the $200 you already paid, the company pays out negative $249,800 times the probability that you die, which is 1 minus the probability that you live. These have to add up to 1. It's a probability distribution. And we multiply across again. And then we add down. That is this formula. That tells us that we multiply the x value times the probability to get the expected value. So we do the same thing for the guys. The only thing that changes for the guys is the probability. Probability of a guy dying is a little bit higher because, well, we're idiots. So 200 times 0.99329 and negative 249,800 times 0.000671. And we add those up. So on average, the insurance company, when charging $200 for a $250,000 term policy, earns $130.25 on teenage females, but only $32 on teenage males because there's a higher probability that they die. So that's why they do it over time. So we can do this by hand as well if there's only two. Live or die are the only two options. We're going to skip number 6. Random continuous variables. So we have the weight of 3-year-old females closely follow a normal distribution with mean of 30.7 pounds and standard deviation of 3.6. So randomly choose one 3-year-old female and call her weight X. So we've done this before, but we didn't call it probability. We called it proportion. So first one, what is the probability that her weight is exactly 30 pounds? The probability of an exact number in continuous data is 0. Always. Please pop through. There you go. Because what's the probability that you're exactly 30 pounds right now? Exactly 30 pounds, not 30.01 or 30.1. With continuous, you can't be sure. So it's 0, always. So what that means is the probability of x being less than 2 is the same as the probability of x being less than or equal to 2 in continuous data. With discrete data, that's not the case, but this is continuous. Now the rest of this is review. What is the probability that the girl weighs between 25 and 30 pounds? So the work I want to see is our normal distribution. Our mean marked in the middle, 30.7, standard deviation up in the corner, and then the two numbers, or the numbers we're dealing with, 25 to 30, and shading. We want to find the area there. So the probability that x is between 25 and 30, again, these don't matter, and we use our calculator. So if we're using the 84, this isn't the 84, this is, we go to second distribution, and it's normal CDF. Now I know some of us have it a little bit different, but we put in our lower limit, which in this case is 25. Keep clicking on the wrong one. So 25. The upper limit is 30. I want to go from 25 to 30. Then I put in my mean, then my standard deviation. I get a probability of 36.62%. Do not give me just 37%. If you round, I will take off extra points. 36.62%. If we're using the Inspire, we got to get out of here. Control I to get a new page. Calculator. So menu, you can get it from probability or statistics. We want distributions and normal CDF. Lower bound, 25, upper bound, 30, mean, 30.7. standard deviation 3.6, and there we go. Same thing. What is the probability that her weight is at least 30 pounds? At least means 30 or more. So the probability of x is greater than or equal to 30. So again, we label our mean. 30 is on the left side of our mean. So we know, and we're shading to the right because we want greater than. So we know it's going to be over 50. And we label our sigma. And we do the same thing. Except, so we can do second entry, have all this in here, but our lower limit now is 30, and our upper limit is infinity. So I can do second insert, and my version of infinity is just a bunch of 9s. And we get 57.70%. Again, do not give me 58%. If we're using this, we're going from 30, 99999, same thing. So we get 57.71% or something close to that. What is her weight if she's in the 80th percentile? So now we know the shaded part. We know the shaded part is 0.08. We know this part. We know the area. We know the probability. And 80 percentile means that 80% is below, so it's to the left. Still label our mean, our standard deviation, and our x value we don't know. That's what we're trying to find. So this little value here is what we're finding. And how do we go backwards? Well, we use the inverse normal. So second distribution, in norm, 0.8 for our area, comma, our mean, comma, our standard deviation. So 33.73 pounds. If we're using the Inspire, same thing, probability, distributions, inverse normal, area is 0.8 or 0.80, mean is 30.7. It kind of asks you for it instead. And there we go. So 33.7 pounds is what her weight is. And that's what we're looking at in discrete and continuous random variables.